Hello, my name is Abdullah Iman bin Azhar. I'm from group G4I. Today I would like to present integrated project for reaction engineering 1. This is our content for our reaction engineering 1. To start off, I would like to explain about the type reactor and catalyst that we choose. First, PBR, which is packed bed reactor, is used for the steam methane reforming reaction. Why PBR is used? Because PBR reactor is do needs catalyst to occur, where the catalyst that we use is nickel and iron, where it combines with aluminum oxide to produce a catalyst and to speed up the rate of reaction. Moving on to the overall balance for the reactor, when natural gas, which is we specify as methane, and steam combine, which is water, the product will form that the product form is carbon dioxide and hydrogen gas. From this overall reaction, there is actually two reaction, which is steam methane reforming SMR and water gas shift WGS reaction. For steam methane reforming, it is an endothermic reaction where methane react with water to form carbon monoxide and hydrogen gas, whereas water gas shift, which is WGS reaction, is carbon monoxide react with water to form a new product, which is carbon dioxide plus with hydrogen gas. For this experiment, we need to have the highest conversion for hydrogen gas, which is later will be purified. Okay, now in order to calculate the reaction order, which is alpha, and rate constant K for both reaction, the method that we use is a graphical differential method. Now, to use this method, the mole balance of PBR will be differentiated into this linear equation where the slope will be the value of alpha and the y-intercept will be the value of K, which is rate constant. From our result for SMR part, after plotting the ln dW over Fn0 dx versus ln Ca, our reaction order is 1.5, whereas the rate constant is K, which is K, is 214. For the WGS reaction, we plot the same graph, which is ln dW Fc0 dx versus ln Cc, where the reaction order, which is alpha, the value is 1.74, and the rate constant K is 3875.
So, we will continue our presentation with strategy to maximize selectivity and yield of hydrogen. So first, we need to increase the temperature, which will increase the production of hydrogen. This because our reaction is having endothermic reaction, which favors high temperature reaction. So, the higher the temperature, the more hydrogen can be converted. So, we need to use a higher temperature for the reaction, but we must not exceed the limit of the temperature to avoid any damage to the equipment and person in charge. So next, the next strategy is we need to increase the pressure, because if we increase the pressure, we can increase the driving force for permeation of hydrogen in the system. So the higher the pressure, the higher the selectivity of hydrogen than the undesired product. But same case with temperature, we can't exceed the limit because it could damage the equipment and people in charge. So we move on to the next slide. So for the next slide, we will discuss about selectivity and yield in the reactor. So in this reactor, we have two, which is SMR and WGS. So for SMR reactor, the selectivity is the ratio between the desired and undesired product, which is our desired for the reaction in SMR is hydrogen and the undesired is carbon monoxide. So we need to find the flow rate of hydrogen and the flow rate of carbon monoxide that coming out from the reactor. So for this SMR reactor, we get that the value that we obtain is 3. So the ratio of selectivity of hydrogen is 3 to 1 to carbon monoxide. Next is yield. Our yield is the flow rate of desired product over initial flow rate of key reactant, which is our methane at initial flow rate minus by flow rate of key reactant at outlet. So the value that we get for this reactor is 3. So next is for the WGS reactor. The value it's same case with SMR reactor but with different reaction, which is the reaction is carbon monoxide plus H2O, which is steam, will produce carbon dioxide and hydrogen. So our desired product is hydrogen also, and our undesired is carbon dioxide. So our selectivity is 4.076 and the yield also 4.076. So that's all for this selectivity and yield. So we move on to next slide. Optimum operating condition for each reactors. First, we start with SMR. Our optimum temperature is 700 degrees Celsius and the pressure is 1 atm. And our catalyst, the optimum catalyst for this reaction is nickel oxide and aluminum oxide. So for water gas shift reactor, the temperature is 375 degrees Celsius and the pressure is 1 atm. And the catalyst, optimum catalyst is Ceria, CEO2. For our research, we use the same nickel oxide and aluminum oxide, but for the optimum reaction for water gas shift reactor, we need to use Ceria. Lastly, we will discuss about method to calculate the sizing of the reactors. So first and foremost, we need to know the weight of the catalyst must be calculated. So we need to find the value of the weight of the catalyst. So we will using the formula for packed bed reactor, which is W, which is weight of the catalyst, equal to integration of FA node, which is flow rate of inlet flow rate of methane, over negative RA, which is the reaction rate for the reaction. So after we expand the formula, we will get the value of weight of catalyst, that is 28,088.1 kilogram. So after we get the weight of catalyst, we can calculate the value of the volume of the reactor, which is the sizing of the reactor. So for the volume, we will use the formula W equal to V rho 1 minus theta, which is theta is the porosity of the bed effluent. So we can get the value of theta from article. So the value that we get from article is, for the theta is 0.4, and the density from the article is 1870, the density of catalyst. So after we rearrange the formula, we will get volume equal to weight of the catalyst over density multiplied with 1 minus theta. So the final volume for SMR is 25.03 meter cube, and the final volume for WGS is 6.323 meter cube. So I think that's all.
Hi everyone, let me proceed with separation process 2. Before that, I would like to explain about CO2 removal unit. In this case, we have chosen counter-current multi-stage absorption column to be utilized. Several assumptions have been made about this unit, which is the first one is other gases cannot dissolve in the solvent. The amount of solvent in the inlet stream is equal to that of the outlet stream, and the solvent also cannot be vaporized. Shown here on the slides is the manual calculation for CO2 removal unit. In this case, we have used a few modeling equations such as total overall balance and also component balance. In this case also, we have assumed the solvent to be pure when entering the absorption column. Hence, basic calculations have been done to find the outlet stream of the solvent which contains the absorbed molecules. Feed gas stream, we have used the component mole fractions of the outlet stream of water gas shift reactor from before to be used in this stream, which are YCO2 equals to 0.430, YCH4 0.031, YCO 0.003, YH2O 0.106, and also YH2 is equal to 0.430. Then for the V1, when solving it, we use the component balance to solve. Next, we will go into the types of adsorbents, type of adsorption isotherm, the design of adsorption tower, which includes the mass transfer zone, diameter and total height of the column. And last but not least, we will also discuss about the strategies of achieving the 99.9% H2 production. On that note, do you know what is adsorption? If you did not know, please read the definitions given here, because I will skip that and explain about the characteristics of ideal adsorbents. The first one, which is the adsorbents must have large surface area, very porous in structure, have economic value, have high selectivity and adsorption capacity, and adequate adsorption or desorption kinetics for the adsorbate. In this study, we have conducted many research to find the best adsorbents to be used in our project, and we have proposed the pump kernel shell activated carbon, which is also called PKSAC. This is the picture of the pump kernel shell if you are curious what it looks like. This is why we choose this adsorbent. This is because PKSAC have higher affinity for adsorbate, which is CO2, and it is abundantly available in Malaysia and has very low market value, so it can be easily obtained. The surface area and pore volumes of this adsorbent is also found to be much higher than the usual activated carbons, as you can see in the red surface area table here. Next, I will explain about the types of adsorption isotherm that is used for this study. So we have proposed the Redlich-Petersen, which is the mix of Langmuir and Freundlich isotherm. This isotherm incorporates with 3 parameters, and the mechanism of adsorption process to mix and results in multi-layer adsorption. This isotherm is also easy, quick, and precise for fitting the equation, and we found that the pump kernel shell activated carbon is also suitable for the multi-layer adsorption, so it is suitable to be used.
Experimental results of adsorption for Langmuir, Freundlich, and Redlich-Petersen isotherms are as follows. That includes the carbon monoxide, hydrogen, methane, and carbon dioxide. This isotherm model is defined by the following general expression as displayed in the slide. The linear form of the Redlich-Petersen isotherm can also be expressed as ln CE over QE equals to beta ln CE minus ln A. So a plot of ln CE over QE versus ln CE enables the determination of Redlich-Petersen constants, where the beta is the slope and A is the intercept. So here's the graphing method and the calculation method, where for the graphing method, we use the ln CE over Q versus ln CE. And according to the adsorption isotherm data, the ln CE over QE versus ln CE graph was plotted, and it shows a straight line graph. And this proves that the adsorption process using pump kernel shell activated carbon fit with the Redlich-Petersen isotherm. For the calculation method, the parameters are given from the respective article, and the temperature of the system is set to 30 degrees C. Based on the figure above, at 303 Kelvin, the value of the constants are first need to be found between 25 degrees C and 35 degrees C. So the calculations are calculated as followed. The design of adsorption column is important as we need to determine the mass transfer zone, the diameter of adsorption column, and also the total height of the adsorption tower. Not only that, we can also find the hydrogen purity to be achieved as stated in the task given. The mass transfer zone happens when the adsorbent at certain region becomes saturated with the adsorbate molecules in which the active adsorption occurs, and then it moves towards the end of the bed, towards the exit, as you can see from the diagram that we have inserted in the slide. From the parameters given, we can find our new HT prime. So these are the steps for the breakthrough calculations. And by using the parameters and looking at the graph, we can find the new HT prime, which is the 7.797 meter. The high purity hydrogen of 99% can be achieved by using in-house pressure swing adsorption PSA process under steam methane reforming SMR technology. So with the 4 back column that we have designed, and as you can see from the configuration above, the 4 back column has achieved a 99.99% of purity and 85.56 recovery of hydrogen. Thus, the most suitable back column is the 4 back column PSA cycle with the recommended as the configuration above. The strategy to achieve the 99% of hydrogen production are by increasing the initial adsorbate concentration, lower the temperature system, use higher bed height of column, and also smaller particle size of adsorbent. For the desorption and regeneration processes, the definitions and the explanations have been included and provided in the slides.